Welcome back to Fundamentals of DC Circuits. In this video, we're going to discuss series circuits and Kirchhoff's voltage law. The learning objectives for this video are to be able to identify a series circuit, to be able to determine the total resistance, total current, and power in a series circuit, to be able to apply Ohm's law and Kirchhoff's voltage law to a series circuit, and to be able to use a series circuit as a voltage divider. These are all of the tools that will be discussed in this video. First, let's begin with our basic definition of what a series circuit is. A series circuit provides only one path for current between 2 points, so that the current is the same through each series resistor. Here are some examples on the screen of a series circuit, and I often tell my students not to worry about what the circuit looks like, only worry about one thing: follow the path that current will take. If there's only one path, it's a series circuit. It doesn't matter the orientation that the resistors are laid out. So for example, in image A, there's one path for current to follow. So this is a series circuit. If you look at picture B, there's also one path because current will flow from the positive terminal through the first resistor, then the second, then the third. There's only one path to take, so that is a series circuit. The third example, again, there's only one path. Current will begin here and flow through each resistor one at a time. Even though if you were to think about this on a geometric type of basis, these resistors are parallel to each other. If we think about how they're laid out in terms of how we visually look at them, we can make the argument in a geometry setting that these resistors lie on parallel lines. But that's not the definition within a DC circuits class we will use to define whether something is in series or in parallel. There's only one definition of whether two things or a group of things are in series, and that definition is if there's only one path of current to follow. That's it. So don't worry about what the pictures look like. Start from where current enters the circuit, trace that path of current, and ensure that there's only one path. If there is only one path, it is a series circuit. So if we look at picture D, again, another series circuit where there's only one path for current to follow. And again, with picture E, these resistors may not look like they're in series by your first glance, but again, if we follow the path of current, the current has to flow through each resistor one by one. So we would call this a series circuit as well. Everything you see on the screen right now is an example of a series circuit. This is what a series circuit might look like on the breadboard. This might be the diagram you're given, where this is your voltage source. Current will flow through R1, and then to R2, and then through R3, and then through R4, and then through R5. That's your schematic. On the breadboard, here's an example of what that may look like. Here's R1, so somewhere along this column here is where you would supply your voltage source. Current would begin to flow through R1 and into this column here. You've got a jumper wire to carry that current over to this column here, where it's then connected to R2. Current will then flow through R2. Since we've got a jumper wire here, it'll go this way, and then it'll flow through R3, across the bridge, through this jumper wire here, through R4, through this jumper wire here, and through R5. And here is where you would have your circuit connected back to ground so that your circuit would be complete. So keep in mind, a schematic of a series circuit will look quite simple on paper. However, when you build it on the breadboard, it may look something like this. It won't intuitively look like it is a series circuit, and we have to remember the operation of how a breadboard is designed underneath in order to create our circuits. So keep in mind that, again, if we want to form a connection, we need to have two terminals within the same column on the breadboard. That's what causes these to be connected, for example, and that's what allows the current to travel from R1 through the jumper wire and then into R2. For any number of individual resistors connected in series, you can calculate a total resistance of those resistors by simply adding them up together. So our R total, or our equivalent resistance, is simply the sum of each resistor you have that is in series. At any point in a DC series circuit, the current into any given point must equal the current out of that point. Therefore, we have a fundamental principle with a series circuit, and this will always be true. Whenever you have things that are in series, all of those elements in series must have the same current flowing through them. So I can have 3 resistors in series or 100 resistors in series. They all have the same amount of current that flows through them. Below that, you can see 2 diagrams that sort of illustrate that concept. Here we have a picture, and then on the right we have a schematic. They both represent the same thing. If we have some resistors that are in series, and we have those resistors connected to a voltage source, notice my polarity is below, so I know current will begin to flow this way, and then up and around. All 3 of these resistors are going to have the same amount of current because they are in series. It's a defining characteristic of a series circuit. So when we have series circuits, we're going to be applying Ohm's law to be able to find the voltage, current, or resistance of any piece of that circuit. And here are some tips that we're going to use whenever we're analyzing a series circuit. Number 1, the current through any of the resistors is the same as the total current in the circuit. And we'll discuss through some examples how you're going to find that total current and how it applies to the resistors in your circuit. Number 2, you can find that total current by using the applied voltage and the total resistance. Now, this is very important. You can't find the total current unless you know the total resistance first. And again, we'll do an example of that in a minute to illustrate that concept. Number 3, you can find the voltage drop across any resistor by taking the total current multiplied by the resistor value. In general, we're going to take Ohm's law and extend it to just a single resistor, and that's why you have an X here. That X represents any resistor in your circuit. So the voltage across any one of your resistors is equal to the current going through those resistors, which has to be the total current in the circuit because they all have the same amount of current, multiplied by that particular resistor's value. Lastly, there is a polarity associated with the voltage drop across a resistor. Remember that the positive side, or the positive terminal of your polarity, is where current enters, and the negative side is where current exits. In a little bit, we'll be learning about Kirchhoff's voltage law, which will depend on you having correct polarities in your circuit. So we will practice constantly labeling the polarity for each resistor based on the idea that the positive side is where current enters, and the negative side is where current exits. So now we'll start with an example. On the first page of your lecture notes, you have the circuit shown on the screen. Follow along with me as we find the following things. We're going to calculate the total resistance in the circuit, the total current in the circuit, and then the voltage drop for each resistor. We're going to label each voltage drop showing the polarity. Let's begin with calculating the total resistance. Remember that when you have resistors in series, which this is a series circuit, there's only one path for current to take. We're simply going to find the total resistance by adding up all of those resistors that are along the path. That's going to give us 820 ohms plus 220 ohms plus 150 ohms plus 100 ohms for a total of approximately 1.29 kiloohms. Keep in mind that I can draw an equivalent circuit that looks like this, where I can replace all 4 of those resistors with one resistor that's 1.29 kiloohms. These 2 circuits are equivalent and will have all of the same values. Next, we're going to calculate the total current in the circuit. To calculate the total current, you're going to use Ohm's law, which says that current is equal to voltage divided by resistance. The important thing to remember here is that your total resistance is what must be used in your fraction. You can't just take the resistance of a single resistor. You have to add up all the resistors first and then use that total to find the total current. So in this example, the total current would be the 25 volts supplied by the source divided by the total resistance in the circuit, which will give you approximately 19.4 milliamps. That's your total current. When you think about current flow, remember that it leaves the positive terminal of the source and flows around the circuit like this. So this 19.4 milliamps of current begins here, flows through R1, through R2, then through R3, then through R4, and back to the source. Equivalently, that 19.4 milliamps flows through our equivalent circuit here like this. Now we're going to calculate the voltage drop for each resistor. And we're also going to label each voltage drop showing the polarity. Now, in order to find the voltage drop for a single resistor, we simply have to take the current going through that resistor times its resistance value. Since this is a series circuit, the current through all of these resistors has to be the total current, which we've already found. So to find the voltage drop across a single resistor, we're simply going to take the total current and multiply it by each resistor value. So for example, the voltage for resistor 1, notice I have a subscript that says VR1, saying that this is the voltage for resistor 1, is going to be the total current, 19.4 milliamps, multiplied by the resistor value, which is 820 ohms. So the voltage drop across R1 comes out to be 15.9 volts. Here's how we're going to label that. Notice that the current has to flow from the positive terminal of the source and then through the circuit. So where current enters is the positive side, where current exits is the negative side. This is how we'll always label the polarity of every voltage drop. Here's the voltage for R2. Again, take the total current, multiply by the resistor value, you'll get 4.3 volts. Once you get that number, you're also going to label that voltage drop on your diagram. The positive side shows where current enters, the negative side shows where current exits. Here's the voltage for R3. You'll take your total current, multiply by 150 ohms, and get a voltage of 2.9 volts. And here's what the polarity will look like for R3. The current enters on the top and exits on the bottom. Lastly, the voltage for R4 is going to be your 19.4 milliamps times 100 ohms, which is going to give you 1.9 volts. And yes, this is a typo. That should say R4. And the polarity for R4 is shown here. Remember, current enters on the right and exits on the left. That's why the plus and minus look backwards compared to up here. Very important to pay attention to the flow of current in any circuit that you are analyzing. Those polarities mean something, so we always have to make sure that they're labeled correctly. So that ends the first problem on your notes. If you flip to the second page, we're going to do another example where we're going to apply Ohm's law to the circuit on the screen. We're going to start by calculating the voltage across each resistor. Then we're going to calculate the total resistance. And finally, we're going to find the value of the source. Notice the voltage source value is not given. We don't know how much voltage is currently applied. But what we do know is the current through the circuit is 1 milliamp, and we know the value for each resistor. Also, on this particular diagram, the polarities for each voltage drop for R1, R2, and R3 are already given to you. Notice again, the positive side is where current enters the resistor, and the negative side is where current exits. So we'll start by calculating the voltage across each resistor. To do that, we're simply going to use Ohm's law. Ohm's law says that V equals I times R. We know the current through all three of these resistors has to be 1 milliamp. So then we're simply going to take that current and multiply by each resistor value. So VR1 comes out to be 1 volt. And there's my label. VR2 comes out to be 3.3 volts. And there's my label. VR3 comes out to be 4.7 volts. And there's my label. Next, we're going to calculate the total resistance in the circuit. To do this, we're simply going to add up all three resistors. 1 kilo ohm plus 3.3 kilo ohms plus 4.7 kilo ohms gives you a total resistance of 9K. And lastly, we're going to find the value of the source voltage. To do that, we're going to again use Ohm's law. Ohm's law says that the source voltage is equal to the total current times the total resistance. We cannot find the value of the source voltage by just using one of these resistors. We have to use the total current and the total amount of resistance in the circuit in order to figure out what the source voltage must be. In this case, it turns out to be 9 volts. Whenever you have voltage sources in series, the total voltage is equal to the algebraic sum of each individual voltage. Now this word here, algebraic sum, is important because it means we have to consider polarity when we add our voltage sources together. So for example, if I have a 1.5 volt source connected to two other 1.5 volt sources, when I figure out the total voltage from point A to point B, I have to consider the polarity of each source. I have plus 1.5 volts, a plus, and a plus. The plus is on the right side for all three of these sources. That means they all have the same polarity, and I can simply add them all together. But if you look at the next example, I have the same voltage sources, but now this one has been reversed, which means I have a plus 1.5 volts, a negative 1.5 volts, and then another positive 1.5 volts. If I add those together, the first two will cancel out because one is positive and the other is negative. That just leaves a final voltage of 1.5 volts. So keep in mind, polarity is always important. The positive terminal of your source will always be the longer edge. So if the plus and minus are not shown, you can always assume that the longer terminal, the longer edge of your symbol is the positive terminal of your voltage source. Next, we're going to learn a new law. It's called Kirchhoff's voltage law. And here's what it says. The sum of all the voltage drops around a single closed path in a circuit is equal to the total source voltage in that loop. So in a nutshell, what this law means is that if I have a certain voltage that's been supplied, the voltage drops for each component around the single closed path, which would mean the voltage drops for R1, R2, and R3. If I add up these voltage drops, it'll be equal to the source voltage. That's what Kirchhoff's voltage law says. Now, Kirchhoff's voltage law is kind of a lot to say, so we're going to abbreviate that with the term KVL. So from now on, you'll hear me just say KVL. That stands for Kirchhoff's voltage law. Another way to express KVL is to say that the algebraic sum, remember that word algebraic sum, it means we have to add up everything with polarity. The algebraic sum of all the voltages around a single closed path is 0. So for example, if I were to look at the voltages around this path, I would pick a single point. This is my starting point, and I'm going to go around the loop. Whatever symbol for the polarity I hit first tells me whether that polarity is positive or negative. So for example, if I start here and go around the path, I hit a plus first. So I have positive V1, a positive V2, a positive V3, and so on. And as I travel around the path, I get a negative Vs. So if all of these voltages equal this voltage, when I add them all up algebraically, I'll get a sum of 0. So now we're going to practice applying KVL. Flip the page in your notes to this problem on the screen. We're going to determine the value of R4. Now before we start, let's analyze what we've been given. We have a voltage source of 50 volts. The polarity is shown here, which tells me that the current has to flow this way. I have a total current of 10 milliamps given. I know the values for R1, R2, and R3, and the polarities for R1, R2, R3, and R4 have been drawn. If polarities are not drawn on your picture, you can easily add them yourself because you know how to add a polarity based on the direction of current flow. So for this problem, we have to figure out what R4 must be given all of these other pieces of information. To begin, we're going to find the voltage for R1. We can find that by taking the current through R1, which is 10 milliamps, times R1, which is 100 ohms. We know the voltage for R1 is 1 volt. We can repeat this for R2 and R3. So now I know the voltage drops for R1, R2, and R3. And I know that the source voltage, or the voltage that I started out with, was 50 volts. Now I'm going to apply KVL to figure out what the voltage for R4 must have been. In order to do this, you're going to pick a point on the circuit. Pick a point, it doesn't matter what point, pick any point. I'm going to pick this point right here. I'm going to write an equation that sums up all the voltages around this closed path. So the voltages around this closed path going this way would be a positive VR1, the voltage drop for this resistor, plus a positive VR2, the voltage drop for that resistor, plus a positive VR3, the voltage drop for this resistor, plus a positive VR4, voltage drop for that resistor, plus a negative Vs, my source voltage. When I sum up all the voltages around a closed path, you start from this point, write down each voltage you encounter until you get back to where you started, and just include the polarity. Whatever sign you hit first is the polarity, positive or negative. So KVL says that if I take a point along a closed path and write a sum of every voltage drop along that path, it has to equal 0. The other way to think about it is that VR1 plus VR2 plus VR3 plus VR4 has to equal the source, which is 50 volts. You can use some algebra to rearrange this equation to see how that will be true. I can simply add Vs to the other side, and that's how I get that all the voltage drops across the resistor have to be equal to the source. However, it's good form and good practice to always start with an algebraic sum where you go completely around a closed loop, add up each voltage, and sum it up to 0. Now that we have this law put into place, we've used KVL to get an equation, let's fill in what we know. We know R1, we know R2, we know R3, we know the source voltage. We have one thing we don't know, and now we can solve for R4. So now I have found the voltage drop across R4. We're not done with the problem though, because what was the question? The question is, what's the value of R4, not the voltage drop across it. So we're not quite done yet, but we're very close. If I know the voltage across R4, and I know the current going through R4, it has to be 10 milliamps because this is a series circuit, then I can use Ohm's law to figure out the value of R4. Ohm's law says that a resistance is a voltage divided by current. I know the voltage for R4, I know the current through R4, now I can use that to find the actual value of R4. And this is a great example of what you can use KVL to accomplish. It gives you an equation. Once you fill in the things you know, you can use that equation to solve for something that you don't know. Next, we're going to do another example of KVL. We're going to use this circuit shown on the screen, and we're going to determine the unknown voltage drop, V3, in the circuit below. Let's stop and analyze what we've been given. I have two voltage sources in series. Notice my polarities. If I'm going from bottom to top, this one has a positive polarity and this one has an opposite or negative polarity. We'll have to consider those polarities when we do a KVL around this loop. We know that V1 has a voltage drop of 12 volts. We know that V2 has a voltage drop of 6 volts. We don't know V3. Notice we also don't know what resistance values we have for any of the resistors, but that's okay because we don't need them. So we're going to use KVL to determine the voltage drop V3. In order to do this, you're going to pick a point on the circuit. Any point, it doesn't matter. I'm going to pick this point right here. And I'm going to go clockwise around the circuit. You can also go counterclockwise. It doesn't matter which direction you take. It doesn't matter which point on the circuit you start with. Pick any point, travel along that closed path, and write a sum of each voltage according to its polarity. So if I start here and go clockwise, I'd have a positive V1, a positive V2, a positive V3, a positive VS2, and a negative VS1. And now I'm back to where I started. So once I write out that sum, I'm just going to say equals 0 when I get back to where I started. Now I'm going to fill in what I know. I know V1, I know V2, I know VS2, and I know VS1. So now there's one thing that I don't know, and you can use algebra now to solve for V3. V3 will end up being 17 volts. This is how we use KVL to find a missing voltage within a circuit. The next topic we're going to go over today is voltage dividers. The voltage divider is a tool you can use whenever you want to find a voltage drop for a particular resistor in series. The total voltage drop around a single closed path will divide among any resistors you have in series, and it's directly proportional to the value of the resistance. So for this reason, we say that a series circuit can act as a voltage divider. It can divide the voltage proportionally based on resistance values. So if I have a source voltage here that's delivering a certain amount of voltage, that voltage will be dropped. Some voltage will be across this resistor, some voltage will be across that resistor. The amount of voltage that we'll have is dependent on the values of R1 and R2. And because we just talked about KVL, we know that when we add up the voltages for R1 and R2, it has to be equal to what we started with at the source. So the voltage drop across any resistor or combination of resistors in a series circuit is equal to a ratio. And that ratio is the resistance value you want the voltage for divided by the total resistance you have for those elements in series. You take that ratio and you multiply by the source voltage, and this gives you what we call the general voltage divider formula, which you'll see on the screen. This formula basically means if I want the voltage for a specific resistor or a group of resistors that are in series, only for in series. You cannot use this rule for resistors in parallel. But if you have resistors in series and you want to know the voltage for just one resistor in that chain of resistors, you can take that resistor value, divide by the total resistance, and then multiply by your source voltage. You'll have the voltage for just that one resistor. This also works for groups of resistors. Let's say I have 5 resistors in series, but I want the voltage across just 2 of them. I can still use this same formula. This value at the top will be the combination of those 2 resistors that I want the voltage for. So let's do some examples. We're going to calculate the voltage drop across each resistor in the circuit below. And yes, we could do this using Ohm's law, but for now, we're going to just use a voltage divider. To begin, you need to know the total resistance of all elements in series. I have 2 elements in series, so I'm going to add those up, R1 and R2. Now we're going to use that general voltage divider formula first to find the voltage across R1. So we're going to set this up by putting the value of R1 in the numerator and the total resistance in the denominator. This is really important. The numerator has to be the resistance value for the resistor that you want the voltage for. If I want the voltage for R1, my numerator needs to be R1. So this is the numerator and the denominator. Then you multiply that value, that ratio, by the source voltage. So R1 will come out to have a voltage of 6.41 volts. If I were to use a voltage divider to also find R2, I'm simply going to change the numerator from R1 to R2. Then I get that R2 has a voltage of 3.59 volts. Remember that we know KVL is a tool we can use. And if we use KVL, we can say that the voltage drops across these two resistors have to equal what I started with, and we can see that it does. Now we have another problem with several different points, point A, point B, point C, point D. And we're going to determine the voltages between several different combinations of these points using a voltage divider. Now keep in mind, this is a series circuit. We have 3 resistors in series. These points are sort of like a probe that you would connect to the circuit just to measure a voltage. It's not a piece of the circuit that current's going to flow through. This is simply the same thing as like connecting a DMM to point A or point B or point C or point D. What's happening in this circuit is you have a series circuit where current is flowing like this. And these points are just like points where you might connect the DMM. That's it. So first we're going to find the voltage from point A to point B. The first thing we need is the total resistance of the entire chain of things that are in series. I've got 3 things in series, so my total resistance has to have all 3. And then I'm going to set up that ratio where I have the value of R1 divided by the total resistance times the source. That's going to tell me the voltage drop just from point A to point B. Now I'm going to do the voltage drop from point A to point C. Now here's an example where I have a group of resistors and I want to know the voltage for more than one thing in the group. I want to know the voltage from point A to point C, which means I want to know the voltage across R1 and R2 combined. How much is that? So here's what our voltage divider will look like now. You still need to start with the total resistance of all 3 things in series. Then the voltage from point A to point C is going to have a numerator where we combine R1 and R2 together. The denominator is still going to be the total resistance in the circuit, and you're still going to multiply by the source voltage. So when we add R1 and R2 together, we get 9.2K divided by the 12.5K, which is the total. We multiply by your source voltage, and now I have the voltage from point A to point C. So this represents the voltage across both of these resistors combined. Next, we're going to find the voltage from point B to point C. To do this, again, you still have to start by having the total resistance of all of your elements that are in series. And then to find the voltage from point B to point C, our voltage divider will have a numerator of 8.2 kiloohms because that's the only resistance I have from this point to that point. And you're going to divide by the total resistance and then multiply by your source voltage. Lastly, we're going to find the voltage from point B to point D. Start again with your total resistance. The voltage from point B to point D is going to be the voltage across both of these resistors. So the numerator is going to have both of these combined together. Divide by your total resistance and then multiply by the source to get 23 volts. And then point C to D, using a voltage divider, start with your total resistance And your numerator is simply going to be R3 because that's the only resistance you have from point C to point D. If you're wondering if you could have used general subtraction to figure out the voltage from C to D, yes, you can. For example, we've already figured out the voltage across R2. We've figured out the voltage across R2 and R3 combined, so you can simply subtract to figure out the difference for what R3 would be. That's another method of doing this problem. So that's it for voltage dividers for now. Next, we're going to move on to talking about power. Now, we've talked about power in the last lecture video, and we talked about power in terms of the entire amount of power generated in a circuit. We can also take that idea and extend it to find the total amount of power dissipated in just a specific resistor. Let's say that we have a series circuit with 10 resistors, and I want to know the power dissipated in just a single resistor. I can take the power formulas that we've already discussed and extend them to apply to a single resistor. These are the formulas we've already discussed. These ones discuss total power. You can simply refer to the X as a single resistor. Resistor 1, resistor 2, resistor 10, whichever resistor you want. The power for a single resistor when you have a series circuit is the total current squared times that resistor value, or the voltage of that specific resistor times the total current, or the voltage of that specific resistor squared divided by its value squared. Again, this is to find the value or the amount of power dissipated in a specific resistor. Or if you want to find the total power in an entire circuit, you can use these formulas. Notice the formulas haven't changed, the subscripts are the only thing that's different. Instead of finding it for an individual resistor, Rx, we're using the total resistance in the entire circuit. This will give us the total power in the entire circuit. So in our next example, we're going to determine the total power in the series circuit below. And using all the formulas that I just discussed, you have multiple ways of doing this. I'm just going to show you one way. We'll begin by finding the total resistance, and that's simply going to be adding up each resistor in the circuit. Then we can use the total power formula. The one we can use is V squared divided by RT, because we know the value of the voltage source and we just found RT. Yes, you can use Ohm's law to find the current through the circuit and then use one of the other formulas. That's fine too. You'll get the same answer. So here's our total power in the circuit. Another way to find total power is to find the total power for each resistor. And then you can add each individual power for each resistor together, and it will still add up to the total. So you have a choice on which method you want to use when finding total power in a circuit. Our next topic is voltage measurements. Whenever we make a measurement within a circuit, we use something called a ground. A ground is a reference point in all electric circuits. It's the point from which all voltages are measured. So if we measure a voltage, we're always measuring it with respect to where the ground is located on the circuit. It's also considered a common return path for electric current. Current has to have a closed path on which to travel. Your ground is your point at which the current that has entered your circuit returns from where it started, thus completing that path for your circuit. The ground point does not affect the current in the circuit. However, the reference point used for ground will affect the voltages across each resistor with respect to that point. And here's what I mean. Let's say that you're given the schematic of a circuit to build or to analyze. Notice where the ground point is labeled. This ground point could be over here, it could be up here, it could be up here, or it could be here. Moving the ground point won't change how much current is flowing through this circuit. The current will stay the same, but moving the ground point will change the point of view for how we measure a voltage. So it's very important that if we had 10 engineers all looking at this circuit, all 10 engineers need to have the ground point at the same point. Otherwise, if you're calculating a voltage And if my circuit has ground here and your circuit has ground up here, we'll come up with different answers for our voltages across each one of these resistors. In this example, we'll show you how that happens. So we're going to determine the voltages with respect to ground for each of the indicated points below. Now you'll see this phrase a lot, with respect to ground. That means, for example, if I'm measuring a voltage at point A, I'm measuring it from point A to ground, which means I'm measuring the voltage along the entire path from this point to ground. I can either go this way or this way. They'll be the same number. But with respect to ground means that, for example, if I have a DMM, I'm going to put my red clip here and my black clip here, and that will measure the voltage along this entire path from point A all the way to ground. So we're going to determine the voltages with respect to ground for each of the indicated points below. So we're going to find the voltage at point A to ground, point B to ground, C to ground, D to ground, and E to ground. We're going to assume that every resistor has the same voltage drop of 25 volts. So if I take the voltage from point A to ground, that means I have 25 volts here, plus 25 volts here, plus 25 volts here. The voltage from point A to ground is 75 volts. Alternatively, I could have gone this way and said, well, the voltage from point A to ground is 100 volts minus the 25 volts here. 100 minus 25 is 75. Next, we can find the voltage from point B to ground. If I'm going to measure from this point to ground, I'm basically measuring the voltage from this point down to ground. If these two resistors each have a voltage drop of 25 volts, they both have a positive polarity because that's what I'll hit first, that would give me a voltage drop of 50 volts. The voltage drop from point C to ground would just be the voltage across this one resistor with a positive polarity, which would be 25 volts. The voltage from point D to ground would be 0. There's no resistance along this path, therefore there's no voltage. The voltage has to be 0. The voltage from point E to ground, if I'm measuring from this point to ground, I have a negative polarity because I hit the negative sign first as I'm traveling along this path. I have one resistor with a voltage drop of 25 volts. So my voltage from point E to ground would be negative 25 volts. Now what we're going to do is repeat this same problem, but put the ground in a different spot. You'll notice that our voltages now are going to have different values. And this is going to illustrate the point. And the point is that we have to have a common reference point to measure voltage from. And we call that common point ground. So now the ground has been moved to be at point C. So now, if I find the voltage from point A to ground, I'm only finding the voltage along this path now. So now my voltage from point A to ground is 50 volts, 25 here plus 25 here. My voltage from point B to ground only has one resistor along that path, so now that voltage would be 25 volts. Voltage from point C to ground will be 0 volts because that's where the ground is located. Voltage from point D to ground will be a negative 25 volts. And then the voltage from point E to ground will begin here. Our path goes this way. I have two resistors, each with a negative polarity, so negative 25 times 2 will be negative 50 volts. This is why we have to understand where ground is at all times and to make sure that it's common among everyone. Because if we don't all have the same reference point from where we're going to measure a voltage, we will get different values. And that's the importance of ground. Also, keep in mind with my subscripts here, VA means the voltage from point A to ground. I can also have the voltage from point A to B or B to C, things like that. But if the subscript just has one letter, it is always assumed that you're measuring from that point to ground. If the subscript has 2 letters, it's assumed you're measuring just from those 2 points. So the fact that all of my subscripts only have 1 letter automatically indicate I'm measuring from that point to ground. So you're always going to want to know where your ground is, and then reference that point whenever you make a measurement. And that is the end of this video.